Hello, everyone. My name is Zhaokun from Texas A&M, and I'm very excited today for here sharing our recent work, FuncTeller, how well does eFPGA hide functionality? For this work, there is a collaboration between Texas A&M University and UT Dallas. There are various threats in hardware security, and it results in commercial loss in semiconductor industry. And among various threats, there is one, which is hardware IP piracy. For untrusted entities happens on the IC supply chain, they may have access to the design's details like the netlist structure. So thereby, they have access to overbuild the chip and sell those chips into the gray market and thereby gain profit from that. So therefore, how to defeat the hardware IP piracy? It's a common question in both academia and industry. To defeat threats like IP piracy, there's kinds of countermeasures, and one of them is called hardware redaction. And recently, many researchers, they use hardware redaction to protect hardware circuits since they consider hardware redaction is a secure countermeasure to protect the circuits. And actually, our paper, we have a different opinion on this statement. So now let's see how the process for hardware redaction happens on protecting the circuits. So for example, there's an original design created by the designer in the design house. Suppose this circuit is an image processing circuit. If we choose the function to be Gaussian blur, then it can generate this blur image as the golden references. When the defender protect the circuits using hardware redaction, so some of the circuitry, it will be replaced from ASIC structure to black box eFPGA structure. So basically for this eFPGA structure, its full name is called embedded FPGA, and in theory, it could support arbitrary functionality. So if the defender applying with the correct bitstream, which is the configuration file containing the design details, then it could generate the image like this, which is the same as the one generated by original circuits. But however, if the attacker, they don't have this bitstream information, then it will generate this dummy image. And we can't tell any objects from this dummy image. In our paper, FuncTeller, it is a reverse engineering tool, and it aims to recover the circuitry that is redacted by the black box eFPGA part. So applying with FuncTeller, we aim to extract the functionality and thereby recover the circuitry with netlist details. So if there's the generate image by the recover circuit, and from the third image we can tell actually recover most of the objects from the image. Now let's see how the process will happens in the global IC supply chain with hardware redaction and FuncTeller. So firstly, a designer, they create the hardware IP inside the design house. Then they pass this layout information to defender, avoid directly sending to the foundry. So that the defender, they can apply with the protection like hardware redaction. Thereby, some of the circuitry is redacted by this black box eFPGA. Then it's secure to send this to foundry. And the foundry will do the fabrication, thereby produce the chip. And notably here, for the structure of ASIC plus black box eFPGA, for eFPGA part, it could support arbitrary functionality. So therefore, after fabrication, they need to send back the chip back to the design house so that the designer or definer, they could apply with the correct bitstream so that to activate the chip. And later on, the foundry will do the further testing and packaging. then the activated chip is ready to sell into the market to end users. And here, for FuncTeller, it considers the attacker as the collusion of untrusted foundry and untrusted end users. So therefore, the attacker can have the chip and obtain the input-output query access to the chip black box part. And after multiple queries into the chip, FuncTeller, it recovers the circuitry protected by black box eFPGA part. So now let's see the high-level approach of FuncTeller. So recall that FuncTeller, it requires the threat model that the attacker have the input-output query access to the chip, which means they can apply arbitrary input pattern and query on the chip and thereby observe the correct output from the output pins. However, there's a challenge exists in this process, which is if the attacker, they want to extract the exact functionality of the chip, they have to query all the query space. So suppose the circuit has n input, then the size of the entire query space will be 2 to the power n, which is exponential to its input size. So therefore, for FuncTeller, if we would like to extract the circuit's functionality, we consider extract its approximate functionality while keeping a good trade-off between efficiency and effectiveness. So the strategy is based on each query, whether the output is a 0 or a 1. FuncTeller, it analyzes and determines the next input pattern to be queried. So with this loop, after multiple queries, FuncTeller, it recovered the functionality of the chip and thereby generate the predicted design. To apply with this predictive functionality happens on the real chip, further, the attacker requires synthesis step. And this process, it could be achieved by many commercial synthesis tools. And therefore, we recover the black box part of the eFPGA protected circuitry. So now let's discuss how FuncTeller predict the design. Suppose there's a circuit with 4 inputs and 1 output. And from the input pins A, B, C, D, attacker, they can arbitrarily choose the input pattern and upload the value through input pins and thereby observe from the output. So suppose firstly, we would like to query with the input pattern of 0, 0, 0, 0, and we found the chip's output is 0 in this case. Then therefore, what happens on the K-map, the left part of the page, in the entry of the query 0, 0, 0, 0, it will fill with this 0 since the output's response. So similarly, we could query with other input patterns, and each time we could observe the output from the chip. And after query on the chip, we record down the results in this K-map example. And here, it's an example with 4 inputs, so the entire search space size, actually it's 2 to the power 4. And from this example, we have 2 observations. So the first observation is we found many of the input patterns resulting output 1, they are clustered together. A second observation is we collect 2 clusters. For multiple clusters, actually they clustered together and closely. So for a random query, the attacker randomly visits the entire Boolean space and do the query so that to fill in this K-map. And FuncTeller, the procedure is a little bit different. Initially, the same. It randomly visits the Boolean space and do the query until the attacker found the first input pattern resulting output 1, and we call it as a seed. So recall that our first observation is input patterns resulting output 1, they are classed together. So here, our goal is we would like to do an expansion from the seed to a cluster. To efficiently query the space, we only query the adjacent entries so that later on we do the first expansion from the seed to a cluster. So record that. Our second observation is clusters, they distribute closely. So therefore, for efficiency, later we would like to search for another seed in the nearby spaces only. So we query the nearby spaces until we found another seed, which is another input pattern resulting output 1. And similarly, we would like to do the expansion. So we query with directions and we realize another expansion. And from this example, we collect 2 clusters on this example. And the random queries, it costs 16 cycles, but for FuncTeller, it's more efficient. And here's an example, happens on 4-dimension space since input size is just 4. But in fact, for most circuits, the input size is much greater than 4. Then for random query, there's the exponential complexity issue. And for FuncTeller, it can dealing with the scalability problem well. So here's the result table showing the performance of FuncTeller on some circuits. It included academic designs and industrial circuits as well. And this result table, it shows the scale of the design, the required attack time, and the accuracy achieved by FuncTeller. And notably, on the IBEX processor, within a reasonable attack time, FuncTeller, it achieved the accuracy of greater than 90% on this processor. So now we would like to understand the column of accuracy. We perform FuncTeller on the real-world application. So we choose an image processing circuit, and there are the 3 images generated. First is generated by the original hardware. The second is generated by the protected circuits, and the others, they are redacted. And the third one is generated by the FuncTeller recover circuit. So here our conclusion is FuncTeller, it works and it breaks hardware redaction on most practical circuits. So this insight is because of the attributes of the circuit's functionality itself. So thank you for listening. This work is supported by DARPA and NSM. Thank you.